I'm live. Great. Yeah, no, I brought the camera back in. I'm leaving it at the desk, so there won't be an issue in that scenario. No. Excellent. Okay, so same as. All right, great. No, that's going to distract me. So here is, again, just a quick reminder of what our layout was to be. I've had to go back a slide, and this is something I went through in week 1 of semester 1. I was meant to have given you your workbook before we finished the first semester, which I didn't. And it was due in for the week of the class test, and I think I know with the full-timers I pushed it out to the week after the class test, so last week to have a look at. I also didn't issue your assignment last week, but that's easier to deal with because I can issue it now, and you can have your breakdown from that, or your time to work from that. And we are going to then have, so your submission for the assignment that I've given you there, the zombie dice assignment, is going to be due for week 5. And then you will have another last take-home assignment in week 9, which will be due for week 12, and you'll have your last class test in week 10. So that's the remaining bits of assessment for this module. Okay. So what I want to cover today is the assignment that I've just put up. I might as well actually show the worksheet as well. Okay, so we look at the workbook first. Ignore the date on it. Because as I said, there isn't really an active date. I'm letting you know it's there now. I'm going to remind you at the start of the class for the next couple of weeks. When we get to the class just before we break for assignment week, I'm going to see how everybody's getting on. If everybody's getting on fine, we might set a date. If people aren't getting on fine, or if there's a lot of other assignments happening at that time, I'm happy to push it out. It needs to be in before the end of semester. My advice is get it out of the way as fast as you can, because it should be quite manageable work for you, and there's no reason to have it hanging over you if you don't need it. Okay, so there are going to be 7 questions on this, and they all relate to methods, characters, and strings. So first one is reasonably small. Create a program to compare 3 letter variables to output the largest. So you can enter in 3 letters, alphabetic letters, and you're going to say which one is going to be the largest. Create a program to increase the letters in your name by 1. So for example, Owen goes to Fuck Joe. Create a program to take a string in from the user, and if the length is greater than 10 characters, you can print out double, otherwise you print out single. So reasonably simple stuff to look at there. Design a function called distance, which takes in 4 fractional numbers, in other words, 4 doubles, and returns back the distance between the 2 points. So between x0 and y0 and x1 and y1, what's the points between that? And you can just look up the calculation for that. There is a typo here. Enable editing. Where are we? Question 5 is create a procedure called print string, which takes in an integer and a string and will print out n copies of string s to the screen, 2 copies per line, except for the possibility of the last line. So if you enter in 5, it'll print 2, 2, and then 1. So if you enter in 5 and hello, it'll go hello, 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 and then the last line will just be hello. Does that make sense? Question 6, called numText. It's going to take in an integer and it will return back the word there. So it'll take in a number that's going to assume to be between the range of 0 to 9. So for example, if you entered in 4, the number 4 into that, it would return back the word 4. So it just stringifies your number to the word that it is. And the last method, which is going to be, or the last question, which would be probably the most complicated of them, is a method called Encode, which is essentially implementing a Caesar cipher. So you're going to take in a string, and you're going to take in an integer, and you're going to shift up all of the letters in that string by that value. So for example, if you go hello world and 1, it shifts all the letters in hello world up by 1. If you do it by 2, obviously it shifts it by 2. The key one here, the key one here is if we take hello world 4 and we shift it up by 4, most of the letters are fine. But if you notice that W, if you move that 4 characters forward in the alphabet, it goes off the end of the alphabet essentially to the 27th letter. So it should loop back around. So the trick with this is that if you go past Z, it should continue on counting from the beginning of the alphabet. Okay, so that's your worksheet. I'm not going to dwell too much on that today because we have time to look at that. Have a read of it over the next week, and if you have any questions, I'll have time to take questions on that next week. But like I said, keep working away and keep doing the bits you can do when you have time. You're probably not going to have time for a while with programming because I'm about to issue you a 3-week assignment. But if you have space to kind of sit down and quickly work through a couple of the questions, I would advise doing that when you can. Okay, close that out. No. Okay, so here is your larger assignment. So it's going to be worth 10% of the subject. It's due on the 12th of March, so the week just before assignment week. Depending on how your assessments are going for other modules, there might be a little bit of flexibility. That's still set to be the class the Tuesday. If it needs to be pushed forward so you get the weekend benefit, I actually don't have a problem with that. But it needs to match up with the assignments you have from other lecturers. So if you have a load of assessment due that week, I don't mind moving it forward. If you have a load of assessment due in the following week and I do push it forward, obviously that's your own time management to figure out how you get all of that assessment in. The deadline is the final submission point. It's not the aimed for submission point. And I know saying that you're all laughing at me because I did the exact same thing when I was a student of, well, it's due for that date, so I'm not handing it up before that date. Okay, so this game is called Zombie Dice. It is a real game. You can go to Amazon and buy it, or you can go to Gamers World in Jervis Street and you can buy it as well. It's a very simple game, and it's it's achievable to implement within a console program. And the idea is that you play a zombie, and you're playing with other zombies, and your goal is to eat as many brains as possible, like zombies do. So you're going to take out a number of dice each time, and you're going to roll them. The dice aren't numbered dice. If you can see from the picture either there or on Moodle, you'll see that they have a mixture of footprints, brains, or explosions, which are shotgun blasts, and they have different effects in the game. Because I'm going to guess nobody in this room has played this game, or very few people in this room have played this game, there is a YouTube link of the game being played. It's off a YouTube channel called Tabletop. It brings you through a full iteration of playing the game. It brings you, as they go through it, as anomalies happen, it will highlight what the rules are, why the rules have been implemented. If you're looking it up now, please put it on mute. I don't want to hear Will we. Okay, so here are the rules. There. Okay. Every turn, me, the player, or you, the player, would take 3 dice from the cup. We're going to randomly generate 3 dice. We're going to roll those dice. There are 3 different types of dice in the game. We have red, which are the toughest. They have 3 shotguns per side, 2 footprints, and 1 brain. They're green are the easiest. They have 1 shotgun, 2 footprints, and 3 brains. And yellow is 2, 2, and 2. And what I mean by number of shotguns, number of footprints, number of brains, they are ways of either losing your life in the game or gaining points in the game. So if you have a brain, that means you found the victim you're chasing, you were able to eat their brain. That's 1 point to you. If you get a shotgun, it means that the victim has fought back and they have shot you. So you've lost 1 of your 3 lives for this round. And if you get footprints, your victim has escaped, but you can chase them. If you roll 3 shotguns, your turn is over. You lose whatever score you've built up in this turn, and it moves on to the next player. So if 2 of you are playing, let's say I'm the first person to play, if I take my dice and I roll them and I get 2 brains and 1 shotgun, and then I roll 3 more dice and I get another shotgun and 2 footprints, I need to make a decision. Do I want to roll 3 more dice again and possibly get another shotgun and lose the 2 points I've already accrued? Or do I stop and I essentially bank those points? If you've ever seen Weakest Link, that was the name, where the person, you can have a round where the score is accruing, it's getting larger and larger and larger. And if you say bank, what it does is it keeps that score and it puts it in, it can't be lost, but then the value for each correct answer drops down to a lower value. So the same thing happens here. It's a risk versus reward calculation you do. You're trying to roll the dice as many times as possible, while the statistical likelihood of you rolling 3 shotguns are low. As soon as it starts to rise up, most people will stop because they've got some points and they'll move on to the next person. So you roll the dice, you have a look at what the outcome is. Mixture of brains, shotguns, and footprint. Depending on what you have, your turn might be decided for you. The goal might be over. If you've rolled 3 shotguns in one go and you're particularly unlucky, that's it, your goal's over, next person plays. And it keeps going around until everybody's had a go and it comes back to you for another round. If you roll, let's say, 1 shotgun and 2 brains, you then have a decision. Do I want to roll dice again, or do I want to finish my turn, keep the 2 I've scored, and let someone else have a go? Because it's a race to see who can score 13 fastest, again, it's that risk reward. What do I want to do? Do I want to keep rolling the dice and risk losing whatever score I've built up? Or do I want to do it very slowly, where once I get 1 or 2 marks or 1 or 2 points, keep saving and hope that other people have worse luck than me? Footprints are kept on the table. So what this means is that in the physical version of the game, if you roll a footprint, you would leave that dice on the table and you would pick enough of the other dice out of the cup to bring it back up to 3. You always roll 3 dice, but there's a decision, or there's a, depending on what the previous roll was, you may have to leave some of the dice on the table. And the color of the dice will indicate how risky the next roll is going to be. So if I get 2 red footprints, I probably don't want to go on for another round, because red is the worst dice. It's the most amount of shotguns on it. So it means there's a much higher percentage of me getting a shotgun in the next turn. If I have 2 green dice, I probably do want to roll, because there's more brains than there are shotgun. So the probability of you getting a shotgun on a green dice is lower. And so it's that balance you're working your way through. What I would suggest doing is have a look at that video at some point. It's about 10 minutes in length. And I think it's specifically, that link there is specifically set to jump to where the video starts. The video's about half an hour length. They do several games. So that's just one of the games they have in there. I would suggest that you have if you have a smartphone, that you have a look at Steve Jackson Games' website, where there's links to the App Store version of them. So you can have a digital version, you can see how the game plays. I'm a fool and I forgot to bring in my physical copy of the game, but I will bring it in next week so you can actually, I'll allot some time so you can play the game then, just to figure out how it's working, okay? If you really want to buy the game, you don't need to, but if you really want to, it's about £13 on Amazon. I think it's about €15 in Gamers World. I am sure the comic shops around town probably have copies of it as well. Okay, deliverables. This is initially spec'd as a team assignment. This spec sheet here, this brief here, is mainly for the full-timers, and I have a lot more of them, so I said groups of 3. For part-timers, I usually go with groups of 2. If you know your work schedule is going to be crazy over the next couple of weeks, if you want to do a team of 1, that's fine as well. If what I need to know is, I need to know who is in what team. So if you have a team of 3 people, I'll work with that. Actually, no, for part-time, we don't have, if this is a full class for you guys, let's go with teams of 2. If there's someone who is on their own, we probably might make 1 team of 3. And if someone wants to work on their own specifically, I will take both the team of 3 and the team of 1 in consideration for adjusting the group grade. Does that make sense? Okay. So I'm looking for 3 pieces of work out of this, not 2 like it says there. First bit is the actual code, the game itself. Okay, so that's going to be a Java program. It's still going to be a console program. It's going to look like all the other Java programs we made through the command line. Okay, you don't need to worry about building the user interface or looking at something like JavaFX or Java Swing or anything like that. Don't worry about that. I just want to see the Java functionality. I want a flowchart or a English explanation of what happens in your game. So what happens when the player first loads the game? What happens after they do the first input? Where, when they take a turn, what happens? What does the player see? Essentially, a user guide to explain to me what's happening in the game. And that will allow me to see how well you understand where information should be moving in that game. You have all completed the systems analysis module for this year. So you have an idea of where information comes into a system, where information is stored or used in a system, and where information exits the system. I'm not expecting data flow diagrams. I don't want EORDs. We're not using databases, so I don't need any of that stuff. But I want some sort of representation to show me what happens in a typical game. It can be a flow chart. It can be a series of bullet points. It can be a paragraph or 2 of text. But just something that explains to me what the game does. And then the last part is a very small report, which I will give you a template for, of each team member's work distribution. If it's a piece of teamwork, I want to see that there was some element of teamwork. I will point out now, although this is never really an issue with part-time students, this is a programming class, so no matter who's on your team and what they say they will or will not do, everybody has to do some programming. Okay, because in the full-time group, I've always got at least one group that said, well, I did all the design and they did all the programming. The programming class, you have to do some programming. Because we have gone through the idea of methods, I would advise you, when you see the mark scheme, I would advise you to splitting up your project into methods and assigning the methods to different people in your team, and yourself to the person, so that you can see who the work distribution is. And try to have it as even as possible. There are always going to be methods which you think are harder than they're going to be, and they end up being very easy, and vice versa. And probably there'll be an uneven amount. Try to make sure everybody's doing as even as possible amount of work. And that's going to be worth 10%. And obviously, like I said, if your team ends up being a team of 3, so you've got one more person, or you're a team of 1 and you've got one less person, I will take that into consideration with the work distribution and how it's broken down. The teamwork element is quite small, and small specifically because you're only in first year. Again, because the full-timers and the part-timers get the same assessment, you're probably going to get far better at teamwork and communication and meeting deadlines and work distribution than the full-timers. But if you haven't had the experience of working in a team, you need to get that experience and you need to slowly build it up. So 10% of a 10% assignment means that if you mess your teamwork up completely, or if you say, hey, I'm doing it all on my own, I don't want to work with anyone else, you're losing a whopping 1% from the total of the course. Okay, so it's not a big percentage in that sense. Okay, learning outcomes. That's just from our module descriptor, what learning outcomes this assignment addresses. Essentially, in English, it's saying you will be able to write a program that's going to work. It's going to be written in some sort of compilable code. For me, it's going to be Java. It's going to be written in correct language, so it's going to actually work. There'll be semicolons where there should be semicolons, brackets where there should be brackets, and so on. You will know where to use a loop or an array or an if statement or a data source or whatever you use, and you can give me some sort of documentation on it, a combination of comments and your flow chart or design diagram, design document. That's the academic way of describing all of it. You can give me a program that works and some sort of explanation of how it works. Okay, here's my grading matrix. The game itself is worth 50% of the total mark going to be awarded. Hey, Tom. Yeah, sure. Okay. So it's, you normally log on to your crypto.ie email address. Yes. So if that's the same password, it should work.
Yes. So it's easier for them to connect to it. Then
Oh, right, downstairs.
Just in this lab.
Oh, this up here.
I was asking you for
This
you.
button. Oh, yeah, this button here. So I can just leave it on.
Oh, if you would.
Yeah. No, are you on a laptop? Or are you on
I know on the computer itself.
Right,
And
now.
that was a problem. I think it wouldn't connect up.
Let's see. I changed my input. Yeah, okay, right. So I will leave it connected to that.
I'll give you 2 minutes earlier now.
No worries. Yeah.
Thank you very much, Emma.
Okay, so 50% of the grade is going for the actual game system itself. The game system is broken down by generating the dice, actually having the array to store the dice. This assignment is focusing on arrays. Okay, if you have prior programming experience, or if you've read ahead, or if you've read wider than this course, and you've started looking at things like array lists, or vectors, or sets, or maps, that's great. But I want to assess how well you know arrays. Okay, I'm just pointing that out, that if you do everything in array lists, it doesn't mean you're going to get the best grade in the class. I want to be able to assess how arrays work and your understanding of how arrays work. So generating the dice is worth 5 marks. Rolling the dice, essentially generating a random number within the range of how many sides the dice has, is worth 5 marks. Adding scores is worth 5 marks. Tracking the number of shotguns is worth 5 marks. So you're tracking until they hit 3, and then you're saying, hey, your go's over, someone else's turn. User ending the turn is worth 5 marks. So the user ending the turn is where I make the decision. It's not worth the risk to try roll dice again. I'm going to stop now and bank the score that I have. The game ending the turn is when you hit those 3 shotgun blasts and they say, right, your go's over, it's the next person. To continue playing, so being given the player the choice to say, do you want to try again? That's worth 5 marks. Having a turn-based system, player 1, player 2, player 3, player 4, player 1, player 2, player 3, player 4, until one of you hit a winning condition, is worth 10 marks. And ending the game, knowing when one of you have hit 13 brains, is worth 5 marks. Okay, so that's the 50 marks going there. User interface is worth 10%. So game style layout is worth 5%. And what I mean by that is, yes, you're developing a game that's going to be based in the console. Try to have it looking a little bit nice. I've got some phenomenal console projects that if this was kind of the late 80s, early 90s, we could probably have published again. And I've got some ones that are horrific. Most of you, when you've given me work back, it has been presented well. There's enough spacing between the output so I can say, oh, that's one output, that's another output there. It makes sense what we're doing. But it's only worth 5%. Don't put hours of work into the output, into the UI. Make it clear, make it readable. Get someone, when the game's finished, get someone else to play it, see if they understand. You don't need to show them the code if it's one of your classmates. But get someone else to play the game. Oh, yeah, I can see what's happening here. Ideally, get someone who's not technical to play the game. If they can understand it, that's a good interface. Displaying the current players worth 2 marks. And then giving user feedback. When something happens in the game, the user should get feedback. You rolled a shotgun. You only have 2 lives left. You rolled 3 shotguns. Your turn is over. It's now player 2's turn. You roll 2 brains. Your current score is whatever. Coding styles worth 20%. So indentations worth 3%. Comments are worth 4%. The use of methods is worth 3%. Because it's a team assessment, it's going to be pretty tough to do this project without using methods. But it's worth 3% on that. The use of arrays is worth 10% because it's an array-based assignment. So I really do want you to use using arrays. And extra features. In the larger assignment, so in this assignment and in the last assignment I give you, I include a certain amount of marks for extra features. Usually not 20%. But because most of you haven't played this game, or none of you have played this game, I have given you 4 options or 4 things to look at. 3 of them I've actually enumerated true. Okay, so using the footprints correctly is worth 3 marks. You need to read the rules to understand what that is. Taking the player's name. So rather than saying it's player 1's turn, player 2's turn, take the player's name. It's Owen's turn, it's Jeff's turn, it's Mary's turn, it's Susan's turn. Having more than 3 players. If you only have 2 players, if you only have 3 players, if that's hard-coded in, fine. But if you allow the user to say how many players are going to be in the game, and you can enter a number in, and then it does the whole sequence for that many players, then that's going to be worth 3 marks. I'll point out, once in the real version of the game, the physical version of the game, once you go above 5 or 6 players, it's kind of a bit weird playing the game because there's a long rotation. So you're trying to keep track of who's on what score and how close am I, and is it worth the risk? It's quite tricky to cover. So you might want to limit the upper limit of the players. You don't have to, but you might want to. And then I have another 10 marks going for the use of arrays. You have to use arrays in this assignment. I would advise you that when you're storing the dice, both the cup that's got the 13 dice in it and the sides of each dice, because they differ from a red dice to a green dice to a yellow dice, that's a really good place of using arrays, but there are other places where you can use arrays. So if you are using arrays well and in inventive ways and clever ways to solve the problem for you, there's an additional 10 marks that are going for that. So that's the 100 marks for your additive scores. Subtractive scores go as such: a gamed submission. So again, more directed at full-time people, but I'll highlight it to you as well. I have been quite explicit in where the scores are going or where the marks are going. It would be possible, considering there is 10% going for interface, 20% going for just how neatly you write your code, to get about 40% of the marks without doing the actual assignment, without doing the actual game. If that's it, I'm expecting you to submit me a game in whatever element of completeness it is. Okay, so a game is somewhere that has some element of scoring, some element of turn-based system, and a definitive end where we know who has won and who has lost. If I don't have that, it's going to be very tough for me to correct the assignment. So generally what I do to dissuade that is if you give me code where you have, and to be honest, in this, the way I've broken down the marks, you kind of have to actively avoid doing the assignment. Really nice comments, but it's got nothing to do with what Owen's asked. I grade everything and then I subtract 60 away from whatever the grade is. If you give me code that's not compiling, I grade everything and then I subtract 20 marks off whatever it is. So if I grade everything, it's not compiling, and you would have got 58 marks, well then I'm going to take 20 off that and you end up with 38 marks. Does that make sense? If bits of your code aren't working, and as we go deeper into this course, it's more likely that there'll be sections of your program which you've made an attempt at, just wasn't working, comment that element out. Whatever you give me, when I load it up on my machine and hit compile, it should work. If I need to change more than 1 or 2 characters, I consider that not compiling. So very often what happens is someone gives me some source code where the file name is called one thing and the class name is called something else, and it builds it oddly. If that's the case, I don't really consider that. But if, for example, the code is incomplete, you're missing brackets off the bottom, or you just stopped writing midway through a line of code and you've got like an open quotation mark, that's what I would consider non-compiling code. Does that make sense? So I want to make sure that whatever you give to me, because this is, again, part of what we're doing in first year is building habits. I want to make sure that when you're presenting code to myself or to anybody else in the future, it works. It'll run. It might be complete. There might be elements left out, but the version of the code you give me runs. And then what you're doing is if you're asking for feedback, or if you're asking for a team check-in in your work, or if you're asking for advice on your assignment submission, we can run the code, we can see what's there, we can see what isn't there, and then we can go in and actually look at the code. But when I go to correct these, the first thing I do is I load the game, and I play the game. I play every team's game. And then once I've done that, because some of the stuff I'll be able to work out grades from actually playing it, and then I actually go into the source code and I go down through it line by line to work out what have you got in there that I've requested, what are you missing, and I'm able to kind of work out my grade from that. Does that make sense? Okay. Right, okay. So what I would advise you to do is between now and next week, have a look at that video. Figure out who you want to be on your team. I would probably put a post up on Moodle where you can just say, look, our team is, and let's list off the people that are in it. We'll go over teams of 2, just based on the size of the class. I'll bring in the physical game next week, and I'll give 30, 40 minutes at the end of the class so we can actually have a look at it and see how it plays if you want to. And if you have any questions, either via email or phone. Fair enough? Okay. And if any questions occur between now and next week, please do email me because I'll be able to address them. Okay. Oh, these. Right. what I want to talk about today. Last week we talked about the idea of arrays. And so an array is a way of holding a collection of data together, a collection of data types together. So we would bind the array by a data type. So we would say it's an integer array, or it's a double array, or it's a Boolean array. But once we've done that, we have a way of taking a bunch of that data type and treating it as one element. So we can pass it into a method with a single call. We can return it from a method with a single call. We can put it into a loop. We can, and because it's a collection, we can deal with it kind of how we dealt with strings. So we're able to find out how large the array is by calling the .length command. We're able to specifically target elements within the array, so we can go to the first element or the last element or the middle element because it's indexed. It has a numerical positioning system, so you know where values are. You know what's in the first element, the second, the third, and the fourth. And because of that, because we know how large the array is going to be with the .length command, and because we know that it has an indexing system, what we're able to do then is we're able to treat the processing of our arrays very similar to the way we did our strings. So we have this systematic approach of take the first character, first element in the array, do whatever evaluation you're going to do in it, move on to the next one, move on to the next one, move on to the next one, and stop when you get to the end of the array. And we did some examples last week where we looked at different things we can do. We searched the array for the smallest value. We searched the array for the location of the smallest value. We found the total of the array. I think did we find the average? The average is essentially get the total divided by the length of the array. So we went through several things that you can do with it. Because we'd spent so much time with strings, I'm hoping that as a group you're reasonably comfortable with kind of, okay, here's an array, I need to check to see how many odd numbers or how many positive numbers. Actually, let's do that one. Let's see how many odd numbers that we have. So what I'm going to do is I'm going to create an array here. So import Java util asterisk. And I'm going to save this as okay, and then here I'm going to say class odd array. Void main. Thank you. So here I'm just going to say random or is equal to new random. And then I'm going to create an integer array called my array. And that's going to be equal to a new integer array. And inside the square brackets here is where we put the size of this array. So I'm going to say 100 elements. So now what I've done is I've created an integer array that's 100 elements in size. I need to put some values inside that. So what I'm going to do is I'm going to have a for loop. It starts at the first element, keeps going while we haven't reached the end of the array, and increments up one by one. So that's very, very similar to how we dealt with strings. And inside here, I'm going to say my array position I is equal to or dot next int, and we're going to generate numbers between 100 and 1. Okay. So what that loop there does is it goes through every element inside the array, starting at the first element, going to the last element, going one by one through every index. And for each index, it generates a brand new random number, somewhere between 1 and 100. So if I wanted to count how many odd numbers are in the array, what I would end up doing is I'd have a very similar loop to this. Let's copy that for a moment. I also need a new variable here called int odd num 0, where my loop is going to do basically the same thing. It's going to go from the first to the last element in the array. I'm not adding values in, so I can get rid of that. But what I am doing is I'm saying if in this array, the current element, how do we check for odd numbers? Can anyone remember?
Mod.
Exactly, mod what?
2.
Okay, you want to keep going?
Equals 0. Equals 1.
Equals 1. Equals 0, because remember, modulus is what's the remainder afterwards. So if it was modulus 2 is equal to 0, it's when you divide it by 2 that you have nothing left over, which is the definition of an even number. So what we're going to do is equal to 1. Yep, that's it. That's larger than the text there. So if we find a number that is divisible by 2 and leaves 1 left over, so it's an odd number, then we're going to say that our odd number plus plus. We found one more odd number. And so this loop here will go from the first element to the last element of the array. It'll check every single number in there. It'll check to see what the leftover value is when we divide it by 2. And for any of them that has a leftover value of 1, we're going to keep track of that. We're going to count how many we have. So at the very end of the program then, what I can do here is I can have a system.out.print. And I can print out how many odd numbers there are. Okay, so that gives us an indication then of how many we found in our counting. Okay, so the key things here and the key recaps from last week is that's how we declare an array. So that array there, we know it's an array because we have square brackets here. We know it's an integer array because we're using the int data type. It's a new array, and the size goes inside of here. When you're creating an array, you must have the square brackets, and when you're creating it for size, you must use the keyword new, and you must put a size in there. It doesn't have to be a hard-coded number. I've hard-coded 100 there. I have also done other programs, other examples where the user has defined what size the array is going to be, and we create an array of that size. This is how I would navigate through my array. I start at index 0, so I is equal to 0, and I go until the length of the array, and I'm accessing individual points by using that syntax. My array, or whatever the name of the array is, open the square brackets, and the value inside the square bracket indicates where in the array it's going to be. And since this counter variable here is going to go from 0 to 99, all of the indices that we have inside our array, it's perfect for tracking where I'm currently at. Okay, let's test this program. Okay, so that tells me that in that array, and I haven't printed them out because that's a lot of numbers, but in that array, there are 44 odd numbers. If we're to generate it again, because we're generating random numbers, I should get a different number. But did you cover statistical probability in Foundations? You might. Okay, right. So next year you have a whole module on statistics and probability, but the easiest one to think of is if you have to generate 100 numbers and you have to count how many are odd and how many are even. It usually falls 50-50, and the larger the larger the data set. So if we have 1,000 numbers, it'll be closer to 50-50. If we have 1,000,000 numbers, it'll be even closer again. It's the same idea as if you have to flip a coin. If you flip a coin 10 times, you probably get 4 to 6, 6 to 4, 5 to 5 of heads to tails. You flip it 100 times, the percentage gets closer. You flip it 1,000 times, it gets closer again. The same idea is working here. Okay, if I wanted to print out that array, before I actually print out the value, what I would have here is I would just have a system. Here I would have okay. So what I have here is I have deleted some of my. How did I manage to do that? Okay, I don't know what I did, but I ended up deleting the int I. And I also deleted it from here. So you can see that I have 3 loops here to go through the array. The first one goes through the array and fills up all the values. The second one goes through the array and prints out all the values. And the third one goes through the array and searches for values that meet a specific criteria. For us, it's going to be odd numbers. So the loop, the for loop here, is identical in all of them. The only thing that's different is what we're doing inside the loop each time. And that's worth paying attention to, because that will allow you to work your way through array-based questions reasonably easily. Okay, so let's just test this one again. I deleted more than I thought. Okay. So now it prints out the 100 numbers that we have here. And it tells me that I have 44 odd numbers. I run it again. I have 51 odd numbers, and there's the actual numbers that I'm using. Okay, so it gives you an idea of what values are inside there. You don't always have to print out the array, but it's nice for having a look here. Okay, so that's arrays. Before I move on, and again, that's what we covered last week, but before I move on, is everyone reasonably happy with that? Does anyone have any questions? I'm using integers here, but I could use booleans, I could use doubles, I could have an array of strings. One of the, I can't remember to be honest, but I think for this last assignment, the word manipulation assignment I gave you, I'd said you can't use string split. But what string split does is it takes a string and it chops it up into space-separated strings. So if you have a string which is a paragraph of text, so words with spaces in between them, it'll chop that up into just the alphabetic characters and put that into an array. So it'll build an array for you of each individual word. And the reason why I didn't want you using string split is it makes the actual calculations much, much simpler. For real life, much more useful than what I got you to do. But from an academic point of view, I wanted you to go through the reinventing the wheel part because it just gets you more comfortable, allows you to assess do you understand strings and how to manipulate them. But we could have an array of whatever we want. So I could create almost the exact same. I create almost the exact same question, but I could use Boolean rather than integer. Yes.
I want to ask, the number that appeared, it was the random numbers? Those numbers?
These numbers here are the 100 random numbers that I generated to fill my array.
Oh.
And then this number down here is how many of them are odd. Okay? So for the examples we're using, we are looking at the idea of searching through arrays. It makes sense just to stick with integers. It's a nice, easy way of doing it. If I were to change this to double, I could change all the other instances to double as well. So this is a new double array. We're going to create here next double. That's actually all you need. So if I were to save this and run my code one more time. What does not like that? Required, no arguments found. Int. Okay. We can actually leave that as an int. Leave the T in it would work. Okay. So now it generates them as doubles. So we just have the 0.0 on the end of it. I could change this to Booleans. So this true false values. And what I could do here is I would need to make it a little more interesting. What I could say here is if me generating a random number, if this number here is, modulus 2 equals 0. So if it's an even number, well, then I'm going to say this part of my array here is going to be a value of true. So if it's an even number, we'll consider it true. Otherwise, we're going to consider it false. Okay. And here we're going to say if this is equal to false. So we're checking to see if it's equal to false there. If we're to run this now, you can see that I get a whole random amount of true falses, true falses, true falses, and it counts how many of them are equal to false. Okay. That's the idea of using arrays. Once we have a collection, and we kind of already done this with strings, but once we have a collection, there are two things you logically would want to be able to do with it. The first thing we're going to look at is you want to search the array. Hey, here's a collection. Do you have this in your collection? That's usually what you want to check. So what we're going to look at today for the remainder of the lecture is how do you search for an element. Now there is two ways of doing it. There is what's called a linear search, and there is a binary search. The linear search you've already done. When I got you to, in this last assignment you had to count how many spaces, and you started at the beginning, you went one by one by one by one by one through the string, and you counted every time you came across a space. You were searching for spaces. So you've already done a linear search. Start at one end, go all the way to the far end, check every element. A binary search is a little more complicated, but it's as with most things in computing, it's more complicated, but much faster. The stuff that's easier to get your head around, it works, but it's usually slower. And so that's kind of what I want to show you here. The second thing you want to do once you have a collection is you want to order your collection. Has anyone here seen the film High Fidelity, John Cusack film? Okay, so essentially it's about a guy going through relationships, but every time he gets a breakup, he starts reorganizing his record collection. And so he does it alphabetically, and then he does it by genre, and then he does it by year of issue, and then he does it by, he starts coming up with more complex ways of ordering it. But it's a collection, so he wants to know what's in his collection, but he also wants to know a specific order for it. Today, we're going to look at a very quick command to shuffle our array into an ascending order. But when we get to the second half of this semester, we come back after assignment week, we're actually going to look at specific algorithms to do this for us. And the reason why we're looking at algorithms, because usually the question I get from first years is, if you have a one-line command for sorting the array, why do I need to learn 3 different ways of doing it? And that's only in first year. In the second year, you learn another 4 different ways of learning it or doing it. And as you move your way through it, you'll learn more and more complicated ways of sorting. So the reason why you do this is in second year, you have a course on data structures, which are classic and agreed upon ways of solving problems within programming. And they're language agnostic. It doesn't matter what language you're using, they're applicable in all these languages. And so we're introducing the idea of data structures this year with our sorting algorithms, and then we get more complicated and therefore faster ones next year, and then that goes on to third year and on to fourth year as well. So it's kind of a brief introduction to our data structures. Okay, so let me show you what linear search looks like. Let's save that and create a new file. Okay, so I'm going to leave a lot of this code the same. I'm actually going to change this back to integer because otherwise it'll be really quick. Excuse me, to search. Right to find. I'm going to populate the array. That's fine. This should be different to this. Oh, for God's sake. Okay, so I'm just trying to get this back to just the starting code that we had. Okay, that's fine there. Right. So what I've done is I have left some elements in from the last one. I'm creating a 100 element array. I have a random number generator, and I'm going to populate this with a value defined. So I'm going to create a value for that in a moment. I'll look for actually, let's go for 67. That's the number I'm going to look for. I'm actually going to fill my array with values between 1 and 100. So I know that 67 has a possibility of being in there. I'm going to print out the array so we can see what values I have. And now I need to search the array. So think about the code you wrote when you were searching for spaces or for full stops in your last assignment. So you do your char c is equal to char at I. So that's your counter, get the current character you're looking at. And then you would have a check. If c is equal to space or is equal to full stop, we're going to do basically the same thing. We don't need to do the char at command because we're dealing with an array. But what we can say is if the current position in my array is equal to the value to find, well, then I found my value. So what I can say here then is, let's give it a print out, system.out.print. You can tell us where it was. So what's going to happen here, well, we'll leave that there for a moment. So what's going to happen now in that last loop is it's going to start at the first element. It's going to go all the way to the end of that array. It's going to check them one by one, and it's going to check every element to see if it's what I'm looking for. So it's the equivalent of having a card, a picture of somebody, and going, no, no, no. Yeah, found. So that's essentially what we're going to do. Now, I did 4 people there, so you get the idea of what I'm doing. If I did it in this class here, it would take a little bit longer. If I went around every room on campus, it would take longer again. So the upside of a linear array or a linear search is it's pretty easy to get your head around what's happening. Check every element. Are you this? No. Okay, move on to the next one. Or are you this? Yes. Well done, you found it. The problem, the downside with our linear search is the larger this array gets, the longer it takes. For us as humans, we won't notice the difference. Okay, so we'll do an array of 100, and then I'll bring it up to 10,000, and then I'll bring it up to 10 million. Okay, so they're reasonable jumps in size. But realistically, we're going to notice a couple of seconds of a difference, not a huge amount. But in relation to a computer, a couple of seconds is a huge amount of time. At the moment, I'm doing the algorithm analysis stuff with second years, so what you'll be doing next year. And we're not dealing with milliseconds, we're dealing with nanoseconds. So it's that 1/1,000,000th of 1 second. So having an entire second to wait for it to do 10 million searches is a ridiculously large amount of time. We don't look at the actual speed of our algorithms or measure the speed of our algorithms in first year, but binary search, you'll see the trade-off or the improvement when we go to that. Okay, so if I run this code now, it's going to go fill the array, print the array, and then tell me where it's found it. What's going to happen here, I also need to put one of these here. What's also going to happen is if I find duplicates, it'll tell me every scenario where I found one. I don't always want to find duplicates. I might just be looking for the first occurrence, or does it exist at all? It's an entirely different reason why you'd want to know how many duplicates are in your array. But for us, I just want to see, does this value exist at all? So let's save that, go back into my code here, and go Java C, linear search. Java, linear search. Okay, so here are my 100 numbers, and 67 was found in value 26, so there's the first one there. It's found in 49, which is going to be there, and it was found in 78, which is going to be there. Okay, so we can see that in the values are there, and that was almost instantaneous. So I run that again, it's pretty fast. The most expensive thing in that is actually printing out the values. If I were to get rid of the printing statement, and this is a good rule of thumb for any work you're going to ahead of time, having printout statements in there to help you as the programmer is great, but hide all of them, comment them all out, delete them out of your code when you're ready to submit your code and you don't need them, because they do slow down your program. So if I run this again now, I didn't find it at all there, found it there, didn't find it there, found it twice there, found it 4 times there, found it once there. Okay, so you can see it's almost instantaneous. If I increase the size of my array to 10,000, increase the number generation I can do to 1,000, so jumping from 100 to 10,000 had very little effect that was noticeable. If I were to increase that then to, that's 10,000, that is 100,000, that's 1 million, that's 10 million, and let's say 10,000. I'm only looking for a single value between 10,000. If I was to do that, okay, when we have 10 million, there's going to be a sizable amount that we found. But even with that, jumping from 100 to 10 million is a huge jump in size, and it was still almost instantaneous that it was working its way through the program. If I were to, and you can see that we found it a lot, if I were to get rid of the printout statement here and just have a counter, so you can 0, and every time I find that, counter plus plus, so that will massively reduce how many printout statements I have and move this one printout statement outside that loop. So at the very end, I'm going to print out the value is found this many times. Okay, so we have a single printout statement rather than possibly loads. Now if I run this code, 10 million values searched through in what was probably 1.5 seconds, maybe 2 seconds of an output. Okay, so printing is massively expensive. You can usually, if you have a lot of printout statements, like we had in the previous example there, by trimming them out, it works far, far faster. And we don't need to. At the moment, we're printing out to help us to verify our code's working. But as a programmer, you don't always need to print stuff out. It might be a case if you're sending it back to a different variable or a different method to be working somewhere else. And for one last time, just to max out how many values you have here, let's create an array that is going to be, what's that? 10, 100, 1,000, 10,000, 100,000, 1 million, 10 million, 100 million, a billion. Fair enough. Let's bring it down to 100 million. Okay, so there was a pause there. 100 million, there was a noticeable pause. You saw that when we went one more above that, and we went to 1,000 million or a billion, we actually got an out of memory error. So we exceeded what the acceptable amount of memory we were using for our searching was. Okay. Ignore that messing around with size and seeing how long it takes to search. That's what linear searching is. You have an item you're looking for, and you are going to start at one end of the array, and you're going to go all the way to the opposite end of the array to see can you find it. In the code we wrote, If I find it, I count how many times I find it. If I only wanted to find it once, I could speed up or possibly speed up my calculation by, as soon as I find it, stopping that loop. So if my loop, because again, if we think about what this code had to do, with 100 million values, I had to go from 0 or from 1 to 100 million once to populate the array, and then from 1 to 100 million the second time to actually search. You could argue that why wouldn't you do the same thing as you randomly generate the number, see if it matches and count it then? Yes, that would speed it up, but I thought we'd separate it out so you can have the searching element separate there. If I wanted to, what I could have here is that once we find the value, we print it out, and then we can use the break command, which will just stop the loop. That makes things a little bit faster. This again is going for 100, 1,000, 10,000, 100,000, a million, 10 million, 100 million. So now, last time running this, it tells you where the first time it was found. Okay, so again, with 100 million, there's a little bit of a delay because it is up near it's approaching the limit of the space that we can hold. But that's the idea of linear search. Is everybody okay with that? That makes sense? Okay. The next thing I want to talk about is binary search. So binary search is very, very simple. Going back to TV game shows, since we mentioned the weakest link earlier on, there used to be a very old game show called The Price is Right. I'm sure other games did as well. But essentially, you would have an item, you'd have to guess the price, and then the person who was closest would get would get to move on to the next round. And so what binary search is it's kind of like that. You have a search space, so the entirety of your array, and the value you're looking for. And what you do is you take the midpoint in your search space, so the midpoint of the array, the middle value in the array, and you go, the value in the middle of the array, is it bigger or smaller than what I'm looking for? And depending on what it is, you get rid of 1/2 of the search space, 1/2 of the array. And so you minimize. So if this is your whole array, after one check, you're half the size. After a second check, you're 1/4 of the size. After a third check, you're 1/8 of the size. So it massively reduces how many values you have to look for. Now the caveat with that is the only way binary search works is if your array is already sorted, if everything is in sequential order. If it's not in sequential order, you cannot use binary search. You have to use a linear search. So we haven't covered sorting algorithms yet. So I'm going to show you a command that you can apply to an array that automatically sorts it into ascending order for you. Okay, so before I move on, does anyone have any questions on linear search? Is everyone happy enough with it? That didn't sound reassuring. If you do have questions, I reckon we'll finish the binary search and then you can have time to think about it and ask questions. I'll also highlight where I would assess this in the future, so you can be strategic about what you need to ask. Binary search. Okay, so my binary search is going to be almost the same. I'm going to populate my array. I'm not going to use 100 million. I'm going to use 100 values because that's manageable. And I'll generate between 1 and 100. I will print them out, but I won't. So what I need to do now is I need to sort my array. And this is going to be different, so we can get rid of this. Okay. So what I need to do now to sort it is I'm going to call arrays.sort, and we're going to pass in whatever our array is. And that will automatically put everything into ascending order for us, that one line of code. The problem is there is overhead associated with that. It's a quick and easy command, but it mightn't be the most cost-effective command. So for us, for the moment, it's absolutely perfect. For you as a computer scientist going through your career, starting your career and working your way to more complex problems, you are probably going to come across non-academic scenarios, so not just an exam question where I say, hey, use this sorting algorithm, but some scenario where you need to use a suitably fast sorting algorithm. Also, you mightn't be using Java. You could be using Python or C# or C++ or some language that mightn't have this command or an equivalent of this command. So you need to know how to implement a sorting algorithm on your own. Usually, when you have a command like that, it's good, but it's not great. So it's good on space, how much memory it takes to run, how much time it takes to run, but it's usually not great on that. So it might be a little bit sizable in how much the memory footprint is, or it might be takes a reasonable long time compared to something else you might be able to implement by hand. Okay, so let's just verify this works first of all. So we're going to create a 100 element array. We're going to randomly generate values, just like we did in the last example. We're going to sort them, and then we're going to print them out just to make sure they're all in correct order. And there is our array, and you can see that all of those numbers are in ascending order. There's lots of duplicates there, but we're dealing with values which are all in the correct order. This makes it much, much easier. Let me actually say it's just an array of 10, just so you can see it visually on one line. Now, okay, so there are 10 numbers. So effectively, what's going to happen when we go to run our, we're going to do 10 numbers to make this larger. When we go to run our binary search, what's going to happen is it will say, okay, you've got 10 numbers there, and pick the midway point. Let's say it's this one here. Is the number I'm looking for larger, that side, or smaller than the number I've picked? And if it's larger, everything from this value to the start, we ignore, and our search field becomes this size. And then we pick the midpoint again, which will end up in this one. And we'll say, is the number I'm looking for there larger than 83 or smaller than 83? And depending on what it is, I'll go one way or the other way. And so we're halving our search space every time we do a check. So if you think about a linear search and the worst case scenario. So the worst case scenario for any searching algorithm is the value you're looking for is not in that array, which means it'll take n plus 1 checks to work that out. So n being the size of the array, and then one more just to end the loop that's checking for it. So if I've got a 100 element array, it'll take 101 checks to verify it's not there. If I have a 1,000 element array, 1,001. So you can see that's what I call linear. It grows progressively or grows linearly as it moves up. If I have a 100 element array and I use a binary search, first search, and let's say again it's not in the array, so it's the maximum amount of times, it goes from 100 to 50, from 50 to 25, from 25 to 12, from 12 to 6, from 6 to 3, from 3 to 2, from 2 to 1 to 0. Much, much shorter. You're looking at 7 or 8 checks. If you have a 1,000,000 element array, it basically works in the same format. So it's more complicated to get set up. It's a little more code, but it works much, much faster. And then what you do is you see what's the problem. What are you actually trying to solve? Are you verifying it exists in the array? Are you counting how many times it is in the array? Because if you're counting how many times, binary search isn't of any use. Linear search makes much more sense. You also have to decide what is the state of the array when you get it. Is it all random numbers and not sorted? In that scenario, binary search won't work at all. You either have to write an algorithm to sort it for you, or use a command like that, or you have to use linear search. So we have these two different options, and most people say, well, if binary search is faster, just always use that. Not always the solution we need. There also are augmentations. So if I've got a 1,000,000 element array and I need to find how many times a value is in there, I can do a binary search or a binary split once just to get rid of half of it. So now I'm only dealing with 500,000, and then I can do my linear to go through it. So there's, as you start to build up your confidence and your experience in programming, you learn about the cost, the algorithm cost for the code you're writing. And there are trade-offs you can make to say, well, look, this is an acceptable amount of time to run. So I'll keep chopping up the array until I get to this time, and then I can run my linear search. But let's have a look. So we have our sorted array. And again, what we're going to do is we're going to pick the midpoint here, and we're going to say the number I'm looking for, which in this example here was 67. Is that larger or smaller than 69? Well, it's smaller. So my next search area is going to go from here to here. I'm only looking at those 5 numbers. And I'm going to pick the midpoint. And I'm going to say, is 67 larger or smaller than 26? It's larger. So then I'm only actually looking for these 2 numbers. And I pick the midpoint, so I pick a nominal one here, 68. Is 68 larger or smaller than 67? It's larger. Okay. It's the only number left I haven't checked. Is this equal to the number I'm looking for? No. So with very small amount of checks, I can establish pretty quickly that the number I'm looking for is not existing inside this array. So let's go and see how we'd write the code for that. What I need to do is I start off with, here are all the values I need to check. I need to know what's the first and the last index of my range, because they're going to change depending on where the number I'm looking for sits. And I need a way of working at the midpoint. Okay? So the way I'm going to do this is I'm going to create 3 new variables. The first variable is going to be called int start, makes sense. The next variable is going to be called int end, again makes sense. And the last one is going to be called int mid. Start is going to be equal to the first index of the array. The great thing about that is we know that for every single array in existence, the first element is always 0. The first index is always 0. End is going to be equal to the size of the array. So this is going to be equal to my array.length minus 1. It'll be the highest index. So it'll go from index 0 up to index 9. So the end is going to be index 9. And our midway, do you know what would be helpful here? If I use the equal signs. Our midway is going to be the midway point between that. And the easiest way of calculating that, because I know that my search space is going to go from the entire array to half of the array to a different half of the array, the end point and the start point are going to shift throughout the program. So the easiest way to calculate the midpoint is to say start plus end divided by 2. So that's going to give us, to begin with, it's going to give us 0 plus 9, which is 9 divided by 2. And remember, we're dealing with integers, and div2 will give us 4 rather than 4.5. So we go to index 4, which is going to be 0, 1, 2, 3, 4. And that, for our program, is going to be our midpoint to begin with. And we work from there. So that's our setup. We need this to keep track of where our search area is going to be. Okay, so our binary search. We then need to have a loop, which for this time is going to be a while loop. This room seems, although it's not, but it seems longer than the previous one. Is that font, like that's as large as I can make it? Is that okay? Yeah. I'm assuming if it wasn't, you'd start moving progressively closer. Okay, and what we're going to say here is we're going to keep going while our start value is less than or equal to our end value. So what's going to happen is, if we have 2 possible ways of finishing this loop. The first one is the optimal solution. We find the number we're looking for, and that's an if statement inside the loop. The last, or the second way of finishing this loop is we've gone and we've checked every possible position, and it's not in there. And the way we can keep track of that is, to begin with, our search space, the end point and the start point are as far away as possible. And the start point is on the left-hand side, which is this for you, and the end point is on the right-hand side. And as they start moving together, the point where we know we have searched everything is when they cross over, when they swap positions. And so that's essentially what this check is seeing here. If as long as start is a value lower than or equal to end, we're okay. As soon as that differs, whether end goes lower than start or start goes higher than end, then we have a problem. Okay, so that's our loop. Inside our loop, we have our three conditions. First condition is our optimal condition. What's going to happen? If my array midpoint, that middle point that I'm going to pick, if that is equal to the number I'm looking for, which I've called value defined. If that's the case, brilliant. I can print out a congratulations message and stop the loop. Found a value in this position here, and then we can call break. A break will quit the loop, okay? So I only will ever get in here if I find the number. Everything else in the loop is basically narrowing the search space to either find the number or to get to the end of my searching. So that's my first scenario. Well done, you've found the number you're looking for. The next scenario is if it's going to be less than or greater than. I can pick one, so I'm just going to pick less than. If my array mid is less than value defined. So in this scenario here, you're saying that the number you're looking for is larger. So if I pick the midpoint, which is 68 for this array here, that the number I'm looking for is somewhere in this range. So I can get rid of this range here. Or effectively what I'm doing is I'm moving my start point for the next time I'm searching forward. From 0 up further into the array. So what we're going to do here is we're going to say mid, not mid, start is equal to mid plus 1. Can anyone guess why it's mid plus 1 rather than just mid?
Is the mid endpoint like you'll search it initially? So
yeah, that's exactly it. There's no point in setting start to mid because then it's included in the next search point, but that's actually what we check first. So the plus 1 just says, oh, you've already looked at that. Let's move on to the next part. And if it is on the other way, if, for example, in the code I've written there, I pick 68, 67 is lower than that, I actually need to look at these values now. There's no point in looking at 68 again. It'll be less than that. So I'm going to move my end position rather than being here, I'm going to bring it back to here. So it will be end is equal to mid minus 1. Okay, that's not finished, but let's have a look at what we have. We have 3 conditions here. They're the only possible conditions we have. The first condition is what we're looking for. Well done, you found the number. The midway point you've picked is equal to the value we're looking for. The second scenario is it wasn't equal to it, but we know that it's going to be larger than the value we're looking for. In which case, we're going to bring the start from element 0 up to the midway point plus 1. So basically, we're chopping off half of our array. We're shortening or we're halving our search area. And then the only other scenario, if it's not equal to, it's not greater than, well, then that must mean it's less than. And in that scenario, we're doing the same thing. We're chopping off half of our search area by bringing the endpoint from the far side over here to the midpoint minus 1. The last thing we need to do, we have either, if we found the number, well, then the loop's finished. Doesn't matter. Anything else we write in here, it's irrelevant. But that's only ever going to happen once. And if we think of a massive array, 100 million elements, we're going to have at least 20 or 30 checks. So we'll only find the value once and we'll stop. So if we've updated the start or the end point, what we need to do is we need to recalculate the midway point. Because if the midway point starts off in your 0 or for the 0 element and end element, and the middle is there, if we move either one of these sides, the midway point now is in a different position. So we need to recalculate it. And the way we do that is copy and paste. No. Notice a mistake from previous code, and then copy and paste this line down to here. So every time, so this is going to be move, start, search area. So here's the move, end of search area. And we'll spell area right. Here is calculate new midpoint. So every time we go into the loop, until we find the number we're looking for, or until we've expunged all possible values, we are going to update either the start point or the end point. We only ever do one per turn, and then we have to update the new midpoint. Okay, so we're just chopping down what we need each time. So let's save that. So in this scenario here, let's go test it. I have my 10 element array. I have the value I want to look for. I have my track point, so I know where my search area is. I'm going to populate my array. I'm going to sort the array. I'm going to print out the array so it can actually physically verify it, or visually verify it, excuse me. And then I'm going to run my binary search algorithm. So let's save that, go in here. Do that. Yes, that's all still readable. Excellent. Okay, so you can see it didn't print out where I found it because I didn't find it. 76 doesn't exist in that value there. If I run it again, it doesn't exist there, or there, or there. And again, if you think about it, I'm generating random numbers between 1 and 100, but I'm only having 10 possible numbers. So the chances of me getting it are about 10%. Although, there we are. Okay, right, so we found it there in index 4. And Sod's law, the first time it generates 2 of them. But it only tells me one of the values that I found, one of the positions that I found. Okay. So that is binary search. Does anyone have any questions on it? If not, what I'm going to do is I'm going to put it into Jelliet, and so you can see it actually working its way through.
Yes, please.
I've noticed weird glitches with Jelliet, so what do we look for here? It doesn't like random numbers, so I'm going to have to trim out that. And as always, Jelliet looks very odd when you have printed statements. Let's give me a second to tidy this code. Okay, so this is going to be, I was going to hard code these values here. 23. Okay. I don't need printhead statements. Nope, I need the population. I don't need the print. And I don't need this because it doesn't work in Jelliet. Okay, so the command arrays.sort just does not work in Jelliet, so I'm skipping that out. You can see what I've done is I've used array shorthand to manually create my array that I'm looking for. The value I'm looking for is 67, so that's going to be there in the second element. Because we can see the array, I could tell you now that if we know the array, we know that a linear search is going to be faster here. But we don't generally know the values of the array. We don't have the complete information about the array. We might know how large the array is, and we might know whether it's in order or not. So with that information, you need to make a decision on what type of algorithm you look at. Obviously, if you can look for it here, and you can say, oh yeah, I know where it's going to be, you've done the computer's work for you. So it's a balancing act, I suppose. No, I don't need to save it there. Okay, let's have a look at this. Let's compile that. See about any mistakes. No, right. Yes, or, because of course I don't have this, so I don't need to populate. No. Try again. Okay, what's going to happen now is we're going to generate our array. 10 elements. We're going to populate all the values inside that. Can anyone spot the mistake I've made? With the array and the values inside it. It's not in order.
Oh yeah.
It is pointless doing a binary search because I actually don't know. Let's run. I'm going to speed the animation up to reasonably fast. I have no idea whether it'll find this or not because if it's not in order, who knows? So let's run it just to see what happens, and then I'll have to rewrite the array so it's in order. No, it's not going to find it because it's looking at element 7 as the midpoint, which is the wrong, and it's already discarded. It had picked element 4 and decided that 23 is smaller than 67, so it got rid of all of these values here. It actually has thrown out the value I'm looking for because I wasn't using the sorted array. So it'll work its way through that. There, so finished. Didn't print it, didn't find anything. Back to the drawing board. Right, okay, hang on a second. I'm going to be super lazy about this and just put all these into 100s. Which still won't work because it's not bloody ordered. Right, okay. There's our ordered. No, I don't want to save it. There's our ordered array. Run that again. You don't need to have it that fast. Okay. Yep, all those values are in order. Good. The one we're looking for is here, which has been populated this up to our variable there. We'll let this run now. So what it does to calculate the midpoint, takes a start at the end, adds them together, divided by 2. Because it's using a div command with integers, it's how many times 2 goes in evenly, which is 4. Let's say the 0 is 9, yes it is. Okay, so you can see now that the endpoint is going to move closer to the start. The endpoint is going to go from 9 to 3. So we've got rid of a huge chunk of our array immediately. And we now need to recalculate the midpoint, which is going to be 3 plus 2 is 1. So this becomes our midpoint here. Is 67 equal to the value we're looking for? Yes, it is. So we can print out value been found. Okay. I'm going to change the position of 67 in that array just so you can see it going for more than just 2 checks. Okay. So again, it's going through the same array again. Just I've moved the position of it, so it should do 3 checks rather than 2 checks. So even with a small amount of numbers, we only have 10 numbers there, you can see that the speed that it chops away irrelevant values is quite impressive. What we're going to do after this is I'm going to set a much, much larger value, not in Jelly, it's something else. And I'm just going to count how many times the loop iterates. Because we know with a linear loop, if it's a million element array, it'll take a million elements probably to look for it. Whereas if we have a million element array and use the binary search, it will take far less. Okay, so that's our first check there. We're adjusting the midpoint. So our endpoint then has become 3. Our midpoint is going to become 1. we're going to check to see if 47 equals 67. No, it isn't. So now we check to see if the midpoint larger or smaller. So the midpoint, is that smaller than that? Yes, it is. So our start moves up from element 0 up to element 2. And then we're recalculating our mid, 2 plus 3 divided by that. So you can see here in the last scenario, the last search we're going to do, our start point and our end point are actually going to be the same number. That's fine. And then we check our loop. We check to see is 67 equals 67, and we found our value again. Okay, does that make sense? Okay. How are ye finding that concept? Does anyone have any questions on it? Before I go on and I do the actual calculation, see how many pass-throughs it takes. In an exam, whether it be the class test coming up in week 10 or whether it would be the exam in May. If I'm talking about binary search and linear search, there's a limited number of questions that I can ask. I could ask an implementation question. Here is an array. Select the appropriate searching algorithm and implement, write the code for it. So you look at the array, is it sorted? Yes or no. If it isn't, linear search. If it is, binary search. I could ask you to compare what's the difference between a linear search and a binary search. And you'd have to essentially write out the code for both and tell me what's happening and why they're different. I could ask you why or what in what circumstances would you not use a binary search? Or would it be faster to use a binary search over a linear search? All of those questions would be question 1 questions. And what I mean by that is they would be the question 1 in the exam paper is a 40-mark question which spans the entire course. That's compulsory. You have to do question 1. But each of the component parts are somewhere between 2 to 7 marks. So even if you messed it up or you couldn't remember what binary search is, you're not losing a huge chunk out of the exam paper itself. Okay, so that's kind of the type of questions that I'd ask.
How many hours do we have for?
The exams you take in first year are 3 hours. Okay, so the way my exam is, I have to write my exam yet. The way my exam is it's going to be question 1, we're at 40 marks, and then there are, I can't remember if there's 4 or 5 other options of which you need to do 3 questions worth 20 marks each to get your 100 marks for the exam paper. Does that make sense? But as we get closer to the exam, I'll have a breakdown on time and guides and that kind of stuff so you can see where you're meant to be going.
I hope it will be enough.
Time? It should be. It should be. You like the programming in first year. It's not a writing test; it's a thinking test. So, if you've ever been through your kind of your high school, secondary school examinations with whatever your native language is, usually it involves an essay, and you can see this just writing, hands cramping in the right. You won't be doing that with my test. Most people, if there are 5, if they answer 4 questions, and question 1's a big question, it's probably 5 to 6 pages of code writing. There's no essay style answers in mine, or at worst, it's a paragraph of text. So if you're writing 5 or 6 pages of code, it's not a lot. Think about the questions you did in the class test. They would be equivalent in size to what I'd be expecting from an examination question. Okay. Also, you'd be more practiced and more prepared when you get to May for those examinations. So it gives you an idea on if your timing for the class test was that you were writing right up to the very end, then the more you practice, the better you get. But that's probably 3 hours about right. If you're finished much earlier, maybe 3 hours would be more than you need. And it'll be swings and roundabouts. There'll be some questions you'll answer super quick. There'll be some questions which are, let's say you have a half an hour schedule for it, it takes 45 minutes because it's just a tough topic. And then the next question you get through really quick. But I'll talk about exams when we get closer. We're a ways away from close. In relation to class tests, I have them all corrected. I just need to throw them into a spreadsheet and actually upload the results to Moodle, which I will do tomorrow. Okay? Right. The last thing I want to do before we finish up is just give a comparison. I'm going to generate a 1 million element linear array, and we're going to search for a value. We're going to go for a worst case scenario. We're going to look for a value which does not exist in that array. Okay, and then I'm going to do a 1 million element array, and we're going to do a binary search, again searching for an element that doesn't exist, and we're going to count how many times. Actually, we don't need to count the linear array. If we have 1 million elements, and we know, because if I'm randomly generating the numbers, I'll look for a number that's not in that range. We know it's going to take 1 million searches, 1 million checks to do. But for a binary search, let's implement this here. Right, so a binary search, let's create, that's 10, 100, 1,000, 10,000, 100,000, 1 million. We're looking for a value that is not in that array. Okay, we're just going to pick negative. So we're only generating positive numbers, so we're going to pick a number that's guaranteed not to be in the array. I'm also going to add here a counter. No, that's not what I meant to write. And also that's an integer. So I can keep track of how many times this is actually printed out. And inside here, every time I go into the loop, I'm just going to go counter plus plus. All I'm doing is counting how many times you get inside the loop. The counter has no other bearing on the code apart from that. At the very end, I'm going to print out the value of counter. There we are. Okay. So what this should do is it should tell us with 1 million elements how many chops it does before it has searched everywhere. So, okay. I feel like I shouldn't have done this bit. Hang on. What have I done? Well, I probably don't need to print the array. That might speed things up a little bit. And it's the sorted array I'm printing, so it's a huge amount there, right? Okay, 19 chops to get from 1 million to I've searched everything. So if you compare that to our 1 million searches we'd have to do, or 1 million checks we'd have to do with a linear array, you can see why someone would want to do a binary search. Let's actually scale that up just for my own interest, because I haven't done this in a while. And that's 1 million, that's 10 million, that's 100 million, that's a billion. Let's see if it'll let me do a billion. It should, from the point of view of a billion is an acceptable number within integer, but I think creating an array of a billion and randomly generating numbers will give me a memory issue. Let's find out. Yep, so out of memory, right. Let's drop it down to 100 million. Now there's a noticeable delay there, okay, but it actually only took 26 chops to go from 100 million to I've checked everything, rather than 100 million. So even if you imagine, and you could see there was a delay there, when we ran that code, there's a note. If you can notice like any gap between when you hit enter and when the output comes up, that's terrible from a programming point of view. It means there's a lot of churning happening in the background. But if you imagine that each one of those searches took 1 second, so it takes 26 seconds to run. Obviously that's exaggerated, it doesn't take 26 seconds. And then imagine 100 million seconds compared to 26 seconds. Because that's what the search would be if you do a linear search. It's a ridiculous amount of time. Okay. Everyone reasonably okay with the idea of binary search? I'll put up the source code for that. Obviously the video is still recording. So I'll put the source code for that and source code for linear. There's no notes on it because it's working our way through there. I'll put comments up in the code. If it ends up that there is confusion on it, I will create notes for it, but traditionally I haven't. I've just done kind of a code workshop on this. The last thing I want to do just to give you a little bit of immediate feedback on your class test, or faster feedback in the class test, is nope. Hang on 1 second. I just want to very quickly go through your class test, the questions in the class test to be clear, so that we can have a look and just you can get a little bit of feedback on what the what I was looking for in each of those scenarios. Class test part-time. There we are. Okay. I corrected all of yours first, and then I've done the full-timers. So my memory of what you as a group did compared to what the full-timers did is a little bit hazy, so I'll just talk about general issues that I found. Question 1 was, create a program that takes a four-digit number from the user and splits it into individual digits and prints each digit on a new line. So it takes in, for example, 2, 3, 4, 5 and splits it out. You're not to use any variables except for integers in your solution. So what I'm looking for here was a combination of our div and modulus command. The div command would give you the number, the front digit in your search, and then the modulus command would essentially chop that off. So the next time around you're dealing with, if you were dealing with a number between 1,000 and 9,999, but then we'll give you a number between 100 and 999, between 10 and 99, between 1 and 9, or between 0 and 9. That's what I was looking for there. Most common correct answer is that you had 4 separate printout statements where you printed like input div 1000, input is equal to input modulus 1000, input div 100, input is equal to input modulus 100. And you keep working it down. So you hard coded the value 1000, 100, 10, and then what the unit value. The better, more complete answer is where you would see there was a pattern between 1000, 100, 10, and 0, and you have some sort of a variable that you altered through a loop as you went through it. Again, I can't remember as a group how you did, but not everybody got that. From a grading point of view, if everything else was perfect, and you gave me those 4 separate printouts, so you hard-coded the values, you're looking at like a 40 to 45 grade out of 50. If you gave the loop in there, you're looking at 45 to 50. Again, assuming everything else in your code is perfect. The most common error that I got was people treating the input as a string and using dot length. That went through 2 combinations. It went through the first combination where people just ignored this line here and said, enter in anything you want. And they took a string in from the user, and then they just split the string up into individual characters. And that's not too bad. That's kind of, I'm being cheeky. I'm going to give you the right output, but I'm going to ignore this last line there. The more worrying one, and I cannot remember if any of you succumbed to this, but I know some of the full-timers did. You took in an integer off the user, but then you tried using, so if you had int x is equal to scanner.nextInt, so it takes an integer in. That's a number. And then you have a loop that has x.length. So you took in an integer, but then you treated the actual integer variable like a string, which cannot work. We can't do that. But most people got that question correct. The next question. Create a program to take the string in from the user. You can assume it's paragraph English text, and output the average length of the sentence from the string. So what I was looking for here is essentially how well can you remember your assignment? You have a string, you're going to count through that string for the first character to the last character, so linear search. And we are going to count every time we find a space, that's 1 more word, and every time we find a full stop, that's 1 more sentence. Or full stop, question mark, exclamation point. I was happy with either. I didn't give any extra marks for it if you remembered the exclamation point, question mark. And then you divide one into the other. Pretty much everybody got that. If you did question 2, pretty much everybody got that. Where people fell down in their solution was the variables they used for holding the number of words and the number of sentences and how they calculated an average. If you went int number of words, int number of sentences, and then you divided one into the other, it's like our binary search. It'll give you an integer result, which is a pretty inaccurate average. So, and if you had the slight variation of that, is where people would create a new double variable called average, but then have the two integers in their calculation. So the integers are divided by each other on the right-hand side, which is going to give you an integer answer, and then we put it into a double, so this adds a 0.0 onto the end of it. Ideally, what you should have done is that your counter variables should have been doubles as well. With doubles, you can still go plus plus, and it increases by 1 rather than by a percentage. But that's a way of guaranteeing a correct double. That's really the only big mistake that hopped out on that. And then the last question. What have I done there? Design a program that reads in the number n and then outputs all of the factorials up to the number factorials all the numbers up to the number the user entered. So for example, if you enter in 5, it can show you the factorial of 1, then the factorial of 2, then the factorial of 3, then the factorial of 4, and then a 5. So here's the trick. If you look at this calculation, and I was only expecting these numbers here. I was not expecting the actual calculation. That's there just to highlight where these numbers are coming from. But if you look at that calculation, you can see that the factorial of 3 is actually the factorial of 2 multiplied by the current number I'm trying to work out. Look, factorial of 3. The factorial of 4 is actually the factorial of 3 multiplied by number 4. The factorial of 5 is the factorial of 4 multiplied by number 5. So the good solutions to this, the best solution to this, is where you had some sort of a total that started out as 1, because that's always going to be the first number that you're going to count from. And as your counter went up, so you had a loop that went 1, 2, 3, 4, 5, or up to whatever it was. And as you went up, you multiplied the previous answer by just whatever the current counter is. So the previous answer is 1 multiplied by the current counter 2, you get 2 by 1. The previous answer is 2 multiplied by the current counter is 3, you get 3 by 2 by 1, which is 6. And so it works its way that way. There were variations on that, but that was, I suppose, the best implementation of the solution. As a class test, how did you find it? Was it as bad as you felt it was before you sat on the test?
No.
Okay, good. Not the answer as expected, to be honest. Usually people get it's just terrifying. It really is designed to be a tearing the plaster off exercise. Nobody wants to sit a test, especially in programming. Everybody would much rather be in front of a computer typing away. But the reality is, the assessment in Griffith is for programming is pen and paper plastic or pen and paper examinations. So to send you an entire year of take-home assessment, typing in front of a keyboard, and then send you into May, never having practiced this before, and actually going to have to write the test, it's a little unfair. So that's why the two class tests are built into the assessment for this year. Whatever your grade is, and again, I haven't compiled it, so I don't even know the averages for the class. Whatever your grade is, it's contributing to your overall assessment. And actually, do you know what I'll do? After the zombie dice assignment is submitted, I will publish a spreadsheet. You can fill in your grades in, and it will tell you how far you are in the subject so far. It will tell you how close you are to passing the CA so far. It gives you a kind of an idea of how well you get on. And each new assessment you get, you can add into that, and it will kind of keep contributing toward that. As I mentioned before, with the class test, you can get 0. And nobody got 0. I made sure nobody got 0. But you can get 0 in this class test and still come out with an incredibly high grade in this subject. So you could take it as an utter learning experience. I messed that up completely. Refocus for the second one. Build on top of that for the exam in May. And you really could come out with a quite strong grade. I'm sure that was meant to sound more optimistic than it was. But every piece of assessment you do counts toward the grade. Even the assessment, and this is not just for my modules, for any module you're doing. Even the assessment where you don't do great or where you don't pass a particular assessment, it all counts towards your running total at the end. And that's an average across all of the assessment you've taken, or whatever weighting that is, whether it's 5% or 10% or 20%. It all adds up, and it all contributes to that total grade. So if the subject is tough, this one or any other one you're taking, everything you do is adding toward a grade, bringing you closer to that start grade. So don't leave assessment out. But also don't get completely disheartened if you're not successful. Like, for example, if you don't pass this class test, fine. You probably are not going to fail the continuous assessment if you've been doing the assignments and working along. And all you need to do then is for the next class test, learn from the lessons. I need to practice more. I need to physically hand write out stuff without notes, without a computer in front of me, and see how I practice then. And then take those lessons for whatever result you have for the second class test and build on that for the examination again. Okay, I think that's probably enough for me.
The solution?
Yeah, absolutely. So my aim will be that over the next week, I'm going to type up commented solutions for this. I'm also going to show you the test I gave the full timers. I gave 2 variations in their test as well. So you can have all of the questions to have a look at with commented solutions.
Okay.
Okay?
Perfect. Thank you.
If you have any questions on the assignment or anything else, please send me an email. I will be honest, I have not looked at the form, and I've noticed that for one other module I'm teaching, the form is not notifying me when someone posts, so I need to go and double check. So if you have put something up in the form, I apologize. I'm going to go check it later on, and I'll respond to any questions that are there.